Okay, we're exactly at at the start of the session, at the time to start the session. So we're uh, in the session called Mining Software Repositories 6. So welcome everybody. In this session, we're going to have 6 exciting talks. And my name is Sonia Hajduk, and I will be chairing this session. So the session will be run as follows. So we will have all the presentations at the beginning. Each speaker will have 5 minutes for their presentation. And the order we will be following is the order that you can find on the conference website on Researcher. Um, and after all of the speakers will do their presentation, we will have a joint question and answer session for all of the speakers. And to ask the speakers questions, feel free to type them in the chat or to unmute yourself at the end during the Q&A session. And please, if you type the questions in the chat and also when you unmute yourself, please make sure to mention which speaker or which paper the question is referring to. So with that, it is my pleasure to introduce our first speaker, Stefan Herbold, and his talk will be on a fine-grained data set and analysis of tangling in bug fixing commits. Stefan, you can go ahead.
Yes, thank you for your nice introduction. So you already know the paper title, so I won't repeat it. And this is definitely the winner of the unofficial award for the paper with the most co-authors this year at ICSI, with overall 48 authors that we have. So we started with 3 authors. So the first 3 images, so that's myself, Alexander Trauch, and Benjamin Ledl, and we registered our study and then recruited a lot more people to join us. If you're interested in that, we have, for example, a paper at the Ropes workshop next week where we just discuss about the recruitment. But today we want to talk about the contents of our empirical software engineering paper. And basically, this is about tangled changes in bug fixing commits. So this is not a new problem. So that says tangling in bug fixing commits is known since almost a decade, but the question is really how much tangling is there if you look at a really fine-grained level, because prior work always looked at in this file might be something else, and then this file was labeled as tangled. What we did is we marked every single line in over 2,000 bug fixing commits. And for each line, we decided, is this part of the bug fix? Is this part of the test change? Is this part of a documentation change? Is this a refactoring? Is this an unrelated improvement? And as you can imagine, such a task is really hard, especially on the scale. We have over 290,000 lines, and we cared about the data quality. So what we did is every of our 290,000 lines was labeled by 4 independent raters separately. And then we just checked, are at least 3 of them agreeing? If so, then these 3 are probably right. And we assign a label, for example, this line contributes to the bug fix or this is a test. If less than 2 or equal to 2 raters agreed, then we just didn't assign a label. We said, okay, this line is apparently hard to label. There's uncertainty here. So we cannot assign a label. So in our data set, you can be quite sure if we have a label, it's correct. And if we don't have a label, and it was somehow difficult for our participants. And this is our key result. So when we looked at these lines, only about 1/4 of them is actually part of the bug fix. So within bug fixing commits, there's a lot more activity for actually modifying test cases than there is for fixing bug. There are also a lot of other activities. So 14% of the line changes are documentation changes. What's relatively seldom is that we have unrelated improvements. So features are added, for example, or refactorings are performed. These 2 make up only less than 2.5%. And then there's the usual stuff, white space changes or some artifacts in our labeling, because some people label the whole test file as test. Others said also looked at the white spaces in there. But overall, we had a huge part of data where we agreed, and only for about 9% of the lines we didn't agree. This picture, we see 1/4 of the line changes a lot when we change our view. So if you look at only production code, then it's about 50% of the lines. But that's still a strong statement. So even within production code, about half of the changes are not for the bug fix. So there's, for example, a lot of documentation changes going on. For example, then also modifying the documentation to maybe mention this bug fix or the change in functionality to support now the new better version. And well, the other changes outside of production code, that's almost exclusively tests. So there's a bit other stuff going on, mostly documentation or yeah, white space changes, similar stuff, but that's basically tests. So we had a couple of hypotheses in our paper, and one was that fewer than 40% of the lines contribute to the bug fix. So we can be sure that this is relatively true if we consider all code, but on average only for if production code, then it's actually more. So it depends on your view whether you say is this true or not. Then we wondered, can we accurately identify this? If we only consider production code, we're a bit worse than we expected. We had many non-random disagreements which highlight the difficulty. So you might ask yourself, is our data reliable? It is, because when we compute what we expect as mislabels, there should only be 111 wrong lines in our 290,000 lines. That's a small percentage. The rest just doesn't have any label. So it is reliable, we just fail to agree sometimes. So does this have an impact on your work? Probably. So a lot of tangling is malicious, so you cannot automatically find it, like a change within a string. And this cannot be detected automatically and can affect program repair, bug localization, defect prediction. And the impact is huge. In the worst case scenario, about 40% of the lines may be affected, for example, for defect prediction. What's affected depends on exactly the use of data. So for example, not everything uses inducing changes, and then the impact is different. So we actually need warning labels for our data. And there's a lot more to this paper. So it's a very long paper. It's only the rough part. So we looked at the contribution, we had gamification in there, we analyzed corner cases. So if you're interested in this, look at our work, look at our video. We have a bit more in there. And yeah, thank you. And I'm looking forward to your questions later.
Thank you very much, Stefan. Our next speaker is Henry Tang. Henry, feel free to share your screen, and he will be talking to us about using Stack Overflow comment edit pairs to recommend code maintenance changes. Henry, go ahead.
Okay, you can hear me, right?
Yes.
Okay, then I will start. So, I will just continue. So, code maintenance is about improving a code base, and sometimes there are inefficiencies, and sometimes there are bugs that need to be fixed. Excuse me. And sometimes the oh my, excuse me. And sometimes the code is just old. And the way that some tools help assist in code maintenance, they utilize data sets. And these are typically bug fix data sets. And these data sets contain faulty code and fixed code. In this case, on the left here, algorithm 2 has some faulty code in that line 1 condition. So a tool that would assist in code maintenance will look at examples like this, find these kind of patterns, and then in an IDE, for example, would suggest some changes. And here are some examples of bug fix data sets. And what most of these datasets have in common is they utilize a version control system and a bug tracking system to create their data. So commits in the version control system are linked with the bug reports and give 3 important pieces of information: faulty code, fixed code, and then usually a description of what problems the bug was creating and how this code change actually addresses things. So bug fix datasets rely heavily on version control systems and bug reporting systems. However, there's some problem with this type of data. When you rely on version control system and bug fix datasets, you have tangled commits, kind of like what was mentioned in the previous talk. And you don't actually know what is actually related to the bug fix and what is not. And as we saw, again, a lot of the changes are not. The type of data in these datasets are also targeted towards corrective maintenance. And this is because when you rely on bug reports, if there was no visible issue, then a bug report wouldn't be created, and then a lot of these issues wouldn't even be found. However, as we know, there are different kinds of code maintenance, such as preventative maintenance. And lastly, there's no explanation about the fix. Taken out of the bug report context, it may be difficult to determine what was the problem and how the fix helps. Commit messages are unreliable to get the information, as there's no real standard, and developers don't really follow a certain way to write the commit messages. And the bug reports themselves may be quite long and may be difficult to extract a summary. So is there another source of data that we can use for code maintenance datasets just to complement the existing data? And so we explore whether Stack Overflow can be used. Stack Overflow is a question and answer site for programmers to ask questions and receive crowdsourced answers, and these answers themselves can have other users leave comments. So our idea is to find these comment edit pairs, and in these blue boxes is an example of a comment edit pair. So from this example, you can see that edits are a bit more concise. This one edit here is for that single comment, and there's only one or arguably two line changes as well. So these edits are less tangled, and it can be for different kinds of maintenance. Like mentioned before, users can comment on these answers, and it may not be always about there's something wrong with the answer. Maybe there's more efficient alternative that would later be integrated into the answer. And finally, the comments of these comment edit pairs provides an explanation for the fix, as usually the comment describes the problem. This example tells us, right? Like you need to call this method before adding, because if you don't, something else will happen. So we hypothesize that these comment edit pairs have concise fixes, detailed descriptions, and may be potentially for different kinds of maintenance to complement the existing bug fix datasets. So here's an overview of how the algorithm works. Given a comment, we extract all the code all the code terms using regular expressions. And after finding candidate edit, we take the directly previous edit and we extract code terms from both. Then we find the symmetric difference between those two sets of code terms just to see if there are actually changes between the candidate edit and the previous edit. Then we try and match code terms with the comment, and if so, then we have this comment edit pair. So we had 4 research questions. What is the precision of our technique? How tangled are the changes? What types of changes? And what is the usefulness of these comment edit pairs? We use the SLTorrent database, which is just the Stack Overflow dump in SQL tables, and we focus on 5 tags: Java, JavaScript, Android, Python, and PHP, because they had the most answers at the time. And so we found that our average precision was 78%, the average tangledness was 11%. We categorized the comment edit pairs and found that the usefulness is around 27% for the comment edit pairs that we found. And to provide some external validation, we made 15 pull requests to open source GitHub repositories. 10 out of the 15 of them were accepted. And this is an example of one of the pull requests. The comment for the pull request was made, taken verbatim from the comment. And just note that this was just used as external validation and not a comprehensive test of the comment edit pairs. And so as conclusion, we kind of conclude that the comment edit pairs are externally validated. So in summary, we utilize comment edit pairs as a complementary source of data. We verified the precision of our technique, the tangledness of the edits, categorized them, and found their usefulness, and then externally validated it with pull requests. And all of our work can be found here on our artifact page. So thank you.
Thank you very much, Henry. And now we're moving on to the next presentation. So our next presenter is Jiakun Liu. Feel free to share your screen. And his talk is titled An Exploratory Study on the Repeatedly Shared External Links on Stack Overflow. Please go ahead.
Hello, everyone. I'm Liu Jiakun from Zhejiang University. Today, I will talk about the external links that are repeatedly shared on Stack Overflow. Users are encouraged to share knowledge on Stack Overflow to solve programming-related problems. For example, users are encouraged to share code in code blocks, stack snippets, and the hyperlinks that point to the code resources, for example, jsvideo.net. However, when inspecting the code resources on Stack Overflow, previous work focused on extracting the code snippets from the posts and overlooked the code resources shared by links. This practice would introduce bias in previous work. Based on our analysis, external resources are frequently shared on Stack Flow. For example, we observe that 1 out of 12 code resources is shared by external links. In fact, over 80% of the link sharing activities on Stack Flow share external resources, while only 20% of these activities share internal links. However, we observe that the external resources are not equally shared on Stack Flow. Some external links are repeatedly shared for multiple times. For example, this link is shared for over 1,000 times, indicating that this link is related to more than 1,000 questions on Stack Flow. The repeated external links compress the valuable Stack Flow knowledge base. However, this example shows that the links to an external website is repeatedly shared by 3 users. Though some of the answers are on topic, it is not clear whether the repeated external links are self-promotion. The self-promoting repeated external links can make it difficult for developers to find other useful or higher quality answers. The repeated external links also bring risks to Stack Flow. Prior studies have characterized the links on Stack Flow based on the resource types. However, there is no exploratory analysis of the external links that are repeatedly shared on Stack Flow. We observe that less than 20% of the external links are repeated external links. More than half of the occurrences of external links are the repeated external links. We observe that though a large collection of external resources are shared on Stack Flow, only a small proportion of them are frequently reused. That is, most of the links are shared for less than 100 times, and only around 300 links are shared for over 1,000 times. Moreover, text resources are the most repeatedly shared on Stack Flow. External links to visualization resources are the least repeatedly shared external resources. One possible reason is that the images are used to provide visualization examples, and different questions are expected to use visualization examples case by case. We observe that the repeated external links can be shared by the same Stack Flow users for promotion purpose. We suggest that Stack Flow could mark the answers with external links that are repeatedly shared by a limited number of users to notify viewers. Viewers are encouraged to browse more answers when encounter the answers with the external links that are repeatedly shared by a limited number of users. We observe that the repeatedly shared external links can be the information overloading links. We observe that the shared resources can provide comprehensive information, and much of the information is unnecessary to the concerns of the question, that is, can be used to answer other questions. When viewers browse the posts and click the links that point to the resources that contain too much information, we believe it could be time-consuming for users to search for the relevant information from a lengthy web page. In the future, researchers could design an automated tool to retrieve the most relevant information from the content of the linked resources. We also observe that external links that are more repeatedly shared are associated with more revisions. This figure shows that the number of versions that revise the external links and the number of times of sharing external links are significantly correlated. This shows that the use of repeated external links increases the maintenance effort. Stack Flow users have to repeatedly maintain the same repeated external links for multiple times. We encourage Stack Flow could centrally maintain the external links. Users can share the resources that are hosted and maintained by the Stack Flow. This practice can decrease the dependencies on external websites. That's all. Thank you.
Thank you very much. And now we're ready to move on to our next talk. Our next speaker is Jenny Liang. Please go ahead and share your screen. And she's going to be talking to us about mining open source software skills from GitHub activity. Please go ahead.
All right. Can everyone hear me, just to double check?
Yes.
All right, fantastic. All right. So, oh, sorry. Some technical difficulties. All right, let me get started. So my name's Jenny, and today I'll be talking about our paper entitled Towards Mining OSS Skills from GitHub Activity. This was done in collaboration with some amazing folks from Microsoft Research while I was an undergrad at the University of Washington. So let's get started with some background. So when we talk about OSS development, we know that open source software teams require diverse roles and even more diverse skill sets, from maintainers to documentation writers. Furthermore, we know that detecting skills can be used to apply to be in problems in software engineering and open source software, like technical role prediction or job recommendations. However, these prior methods really just focus on detecting technical expertise like skills in programming languages. But this leaves a gap because it doesn't necessarily address how to detect soft skills. And this is notable because soft skills are crucial to OSS development and software development, as seen from prior literature. And so in this work, we really focus on how do we detect skills in OSS development, including both soft skills and hard skills. Our key insight for this work is by identifying relevant measurable activities, or cues, that correspond to OSS-related skills. We call these cues signals. Signals are really grounded in GitHub activity, and so we can really take a look at these artifacts like markdown files, activity around issues, or merging pull requests to kind of identify or generate valid signals. So let's kind of take a look at some examples of signals just to, ground them in more concrete terms. For example, if we're looking at proficiency in Java, we might look at the number of lines of code written in that language. And for communication, we might look at the toxicity score on GitHub comments. So now I'm going to jump into the method and describe how we exactly implemented our key insight. First step is really just identifying valid OSS skills and signals. And so we did this through a literature review of software engineering expertise, social factors of open source software, and mining OSS repositories. We then validated the skills and signals by talking with 3 open source software community experts. We ended up with 4 main skills to kind of try to detect. 1 is teaching others to be involved in the project. 2 is commitment to an OSS project. 3 is being familiar with OSS practices. And 4 is programming language knowledge. And so what we did was then, given these 4 skills, we developed a tool called Disco to detect them. And Disco is a Python tool that queries GitHub API and GHTorrent. And, it takes a GitHub username, and then it outputs skill ratings from 0 to 5 for the 4 skills I mentioned before. Here, 0 represents no experience with the skill, while 5 represents a high proficiency. Disco basically kind of detects skills in 2 main phases. 1 is to mine the actual signals, and then 2 is calculating the proportion of signals present. We then take the proportion and use this in a very simple piecewise function to generate the skill ratings from 0 to 5. So to evaluate Disco, we had a 2-part survey. One part of the survey was to evaluate the relevance of the signals from our literature review. And then the second part was to actually collect a data set of self-rated skills from GitHub users. And we had 316 responses in that survey. We then evaluate Disco on the precision of skill presence and then the precision of high skill proficiency. So in terms of results, what we notice is that skills that Disco detects are important to contributors, and we find that soft skills are actually most important. Furthermore, we find that OSS contributors would publicly display OSS skills, or Disco skills, and we find that actually technical skills here are most important, in contrast to the previous results. In terms of performance, we find that Disco detects the presence of skills with moderate or high precision and high skill proficiency with moderate precision. So with discussion, we find that Disco is a simple and intuitive approach that still yields moderately successful results in detecting OSS-related skills. And so our takeaway is that skills detection is definitely a research direction that others can look further into. Potential impacts include enhancing existing OSS experiences, like matching GitHub users to projects, and we can even extend and make the techniques for detecting skills more refined and advanced by using things like machine learning or interviewing OSS practitioners to find more accurate signals. So that's all I had today. Thank you so much, and I look forward to your questions later.
Thank you so much, Jenny. And as a reminder, you can post questions in the chat in the meantime while we're still watching presentations. And I see questions are starting to appear, so awesome. Okay, so we're ready to move on to the next presentation. Our next presenter is Erdem Tuna, and his talk is about bug tracking processes, smells in practice. Please go ahead.
I'm Erdem Tuna. I'm a graduate student at Bilkent University, and today I will present you our paper, Bug Checking Process Smells in Practice. So let's get started. In a typical software development lifecycle, we have several processes, and development is one of them. And during coding, developers inevitably introduce bugs to software, and it's not rare that software is shipped with many bugs indeed. People may encounter these bugs in different forms, and the existence of bugs in software brought the need of using bug checking systems that provide a medium to run bug checking process in an organized manner. And in a typical bug checking process, we realize many actions such as linking, resolving, assigning, triaging, and etc. And it is mostly the humans conducting these actions, which are sometimes subject to being suboptimal. And suboptimal activities could lead to smells in processes. And there's a recent term, recent study that quantifies the bug checking process smells as the deviations from the best practices in the bug checking process. And in our study, we put the taxonomy of bug checking process smells and detection tools to a test in an industrial setting at JetBrains company, and we defined 4 research questions. So our first research question is about exploring the occurrence or prevalence of bug checking process smells in an industrial setting. And the other 2 are related to understanding developers' view on the bug checking process smell concept. And our last question is to evaluate the potential added value of a tool detecting these bug checking process smells in an automated manner. So let's move on to our study design. We conducted this study at JetBrains company with JetBrains Research, and to mine bug checking data, we used UTrack platform, that is the main issue tracking, or in particular bug checking platform of the company. And we mined bug checking data of 4 projects which have number of bugs from 5,000 up to 150,000. And by using this data set, we found the occurrence ratio of each bug checking process smell. And afterwards, we supported our study by conducting a developer survey where we get the views of developer on bug checking process smells themselves and the severity and other aspects of each bug checking process smell. And in the last phase, we evaluated the potential added value of a tool detecting these bug checking process smells in an automated manner. Let's jump into results. So we generated a heat map on the right that shows the occurrence ratio of each bug checking process smell among 4 projects. And we conclude that the process smells occur in practice in an industrial setting, and the prevalence of each smell depend on the particular practices of teams developing these projects. So as a second research question, we wanted to see if developers agree with the process smells and their definitions. So for 10 out of 12 smells, developers do agree with the definitions of these bug checking process smells and their detection methodologies. But for the last 2, there's a controversy among developers. Next, so developers may agree with the bug checking process smells, but the smells may not have an impact onto their processes. So we asked the severity of each smell, and we found that some smells are considered to be highly severe by developers, and on the other hand, some other smells have considered to have no impact or minor impact to their bug checking processes indeed. So the last question was about whether a tool would be useful detecting these smells in an automated manner. We see a ranking in parallel to the severity perception here. So the top smells here are considered to be very useful when they are detected by a tool, but the other smells at the bottom is in parallel to the severity have considered to be harmful indeed when they are detected by a tool from the developer's point of view. So let's move on to discussion. Indeed, we listed 3 of our implications here, which we have more in the paper. So we conclude that smell detection should be tailored, and practitioners should be involved to make sure that bug checking project interpretations are correct indeed. And we defined, or we identified 2 essential features that a tool detecting these bug checking process smells should have. The first one is the support for tailoring the smell detection, and the second one is actually the visual and statistical interpretation of smell data. So let's conclude our presentation. So we conducted the first study on the occurrence of bug checking process smells in an industrial setting, and we assessed the perception of developers on the bug checking process smells concept. And lastly, we evaluated the potential added value of a tool detecting these bug checking process smells in an automatic manner. So thank you for listening. I'll be happy to answer your questions afterwards.
Thank you very much, Erdem. And our last speaker in this session is Jiang Gwen. Please feel free to share your screen, Jiang. And his
Yes.
talk today is on Manas, which is mining software repositories to assist AutoML. And please go ahead whenever ready.
Yeah, can you hear me?
Yes.
Yeah, so hello everyone. My name is Zhang Wei. So today I'm going to talk about our paper Manas mining software repository to assist AutoML. So this is a collaboration with my lab mate Muhammad Zuhir Islam, Rangi Pan, and my advisor Dr. So deep learning is a class of algorithms that have gained significant popularity in recent years. So deep learning is success in many applications such as internet cloud or media and entertainment. However, there are still many challenges in programming deep learning. The problem is the constructing an appropriate CNN model architecture, which also have been shown as a frequent bug in CNN program by Islam et al. These are some examples from Stack Overflow of the challenge in deep learning. For example, here a developer don't understand why Keras neural network is a learner, or here he doesn't understand why ResNet doesn't work as expected. So AutoML aims to solve this problem, generate appropriate model for given dataset. AutoML takes the training data input to automatically define the neural network that for that data, and moreover, it is able to tune the hyperparameter of the search network. However, AutoML also has some limitations. First, it can be very, for example, neural architecture search is one of AutoML which generate 8 times more amount of carbon footprint than using handmade models. And neural architecture search often produce models that are hard to understand to train. So to the problem of AutoML, we propose a method that leverages software repository mining to reduce the complexity of the model produced without losing accuracy. So as you can see here, AutoML starts with the same default model for all datasets, and it keeps it until it finds the good one. Dataset have different characteristics. We should be started with different default model. Therefore, we propose a method which identify a better initial model. The new initial model, the performance of AutoML in terms of error rate, because like it start from the first iteration. Now AutoML can start from the case iteration. We have a trend to search more amount of model in the same amount of time, which increase the accuracy of AutoML. So to utilize Manas for AutoML, we mined high open source repository. After that, from the mined model, we identify a new initial model for AutoML by using model matching. The intuition being that similar data characteristic can use the similar model architecture to train. And each model is created for certain data set, and it also includes the data this data set. Therefore, we find the suitable model by comparing the data characteristic the mined model with the input data set. And we also have utilized the common pattern to enhance the performance of the new initial model by using model transformation. We transform the initial model architecture applying or adding layers such as byte normalization layer, active or active, and these transformation optimize AutoML in terms of error rates and model complexity. So to evaluate the efficiency of MANAS, we compare the performance of MANAS and AutoGrad in terms of error rates and model complexity. The following graph shows the percentage change of the result of MANAS and AutoGrad in different perspectives. In other words, the positive value MANAS outperform AutoGrad in a certain criteria, and this chart either the of MANAS and AutoGrad in terms of error rates on classification problem. So on average, MANAS outperform AutoGrad 17.6% on classification. And this just either the comparison of MANAS in terms of model complexity on classification problem. So the models from 77.8 to 98.5, fewer number of parameters than our model on classification problem. Yeah. So thank you a lot for the presentation. So for more information, please take a look the paper and the talk.
Thank you very much. So with that, the portion of our session with the presentations has concluded, and now we're open to questions. So we already have a few questions in the chat, so I'm gonna read them out loud, and then I invite the speakers to answer. So the first question is from Masood Rahman, and the question is for Stefan and others. He says, great work on labeling and analyzing the tangled commits. Previously, folks attempted to detect the tangled commits automatically. And he says, we have two choices ahead, costly manual labeling of all tangled commits and automated/cheap labeling with some false positives. Which one should we choose moving forward? Or do we have a third option?
Actually, I would say we're already using the third option quite a lot. So, for example, for program repair, defects for J and basically manually created data sets where this untangling was done are the gold standard. And that's basically what's being used there. So for such a domain where more or less every mislabel and every tangled change can actually have a strong negative impact on your application because you learn a wrong fix and then later you also maybe learn wrong fixes. There, it's already very common to use smaller data sets, but that were manually corrected. For other use cases, so for example, when you look to bug localization or defect prediction, so far there's only very little care about tangling. But the bad thing is that every study that considered whether the tangling has a negative impact says it has a negative impact on the performance. So I think we're a bit of a crossroads here. So we need to decide, do we want to also go to the, let's say, program repair side in this other domain and say, let's rather work with less data, at least for testing our approaches and get more accurate, more valid results? Or do we not care? So overall, our recent work, not only this on tangling, but also issues in Jira, Jira mislabels and so on, says that in a lot of such data set, you have more noise than signal. We can accept that, but this basically means that often we do not localize defects or predict defects, but rather changes. There's a whole line of research that says we're doing change prediction. That would be another third option. And another third option would actually be to use the automatic tangling detection. So basically the papers that are not, we do this within SZZ are completely ignored. And even the improvements to SEZ are mostly ignored by most data sets. So if we would just use these automated approaches and maybe also evaluate them, for example, then on our data set or on other manually untangled data set independently later on, maybe we would be in a better place. So I would say we just need to stop ignoring it and then see where it brings us if we stop ignoring. But it's been there since almost 10 years, the study by Herzig et al., which basically highlighted, and others, I think, a bit earlier, 2 years earlier, and we're still ignoring it. That's kind of, yeah, our fault as a research community. So my third option is stop ignoring it, and then let's see whether option 1 or option 2 is a better choice.
Thank you, Stefan. Does anybody else have any thoughts on this? Any of the other speakers? Masood, was that is that answering your question? You've got a lot of options here that Stefan talked about. So, okay, let's thank you for that. Let's move on to the next question. And this question is for Jiakun. And the question is from Mariam Guizani, and she's asking, can repeatedly shared external links signal a recurring problem finding these types of information? How can we use this data to help make sense, to help make these information easier to find?
Yes, repeatedly shared external links signal a recurring problem finding. In fact, in Meta Stackflow and Meta Stacks Exchange, there are many posts discussing that the repeatedly shared external links indicating the duplicate questions in some terms. And in some cases, that the repeated shared link indicates the duplicate questions. And if you use the repeated links, you can find many duplicate questions when you're searching it on Stackflow. So I would suggest that I suggested that we can use the repeated links to find duplicate questions on Meta Stackflow, but it is not accepted by the Stackflow community. And if we use the repeated links to find when users on Stackflow to mark duplicate questions, they can refer that if the answer of the questions have the repeated links. If so, the questions can be the duplicate questions. And if so, if there are more, if the relation between the questions is illustrated as duplicate questions, and this could make the information finding more easier. That's my think. That's all.
Thank you, Jiakun. So basically, just try to find duplicate questions, and that might solve the issue of having repeated links, because people would not have to keep repeating the same answers, right?
Yes.
Okay, great. Thank you. Thank you very much. The next question is from Henry. Henry, since you're already there and ready with your microphone, you want to just speak your question?
Basically, my question was for Erdem, and it was about the bug tracking smells. And it was just with code smells. I always thought of like issues that could cause potential like larger problems later on, but I wasn't sure how the tracking smells would really cause bigger problems later on if the bugs eventually get fixed anyway, right?
Mm-hmm. So thank you, Henry. So actually, like the code is the product of your software development, and you develop your product as a consequence of your processes or process chains. And in the software, when we consider this process in the context of software development, bug checking is a process on its own, and we can consider bug checking process as its own, and the other processes that it affects too. So related to bug checking process smells, some of the smells are related to the sole process of bug checking. And for instance, when you assign or reassign some developers to the same bug over and over, that's an indication that you are not doing your project planning correctly, or you are overloading some people, so they are not able to complete their bugs, and they have to hand over their bugs, for instance. Or when you have some reopening bugs, that this is an indication that your software development process actually the coding part might be bad, or that might be due to developers' ineffectiveness or ineffective investigation of bugs presence in your software repository. So the bug tracking process smells let you find what are the bottlenecks in your bug checking process and potential effect of bug checking, your potential effect of your bug checking process to your other processes such as project management and software development.
Okay, thanks.
Thank you, Erdem and Henry. We have another question from Mariam Guizani. Thanks, Mariam, for being so active in our discussion. So she says, Jenny, great work. And how do you see this impacting the future of open source software and in helping in project selection?
Oh, okay, cool. Yeah, no, that was a great question. Thanks, Mariam. Really, I don't think I had a chance to really elaborate on this point fully, but I think this definitely, we're envisioning sort of these sort of skills detection approaches, even just aside from what we did, as definitely helping with project selection, right? So theoretically, you could have folks who, have validated skills that we've been able to detect, and you also have folks who are really looking for people with specific skills, right? And through this sort of matching process, we might be able to kind of improve project matching to align, the skills that people already have with skills that, project maintainers are looking for.
Thank you, Jenny. Are there any other questions from the audience? You can, also unmute yourselves and just let us know your questions. How about you guys? You that presented in this session, do you have questions for each other?
Yes, I actually have one. So when we look for changes on Stack Overflow, I think your idea was that they are less tangled, right? And then the data from the paper, I think, said that it was 11% still tangled, even on Stack Overflow. So first of all, why are there tangled changes on Stack Overflow? I mean, are they just randomly copying code snippets there with anything in there, regardless of whether it's answering the question? And then if we still have tangling there, aren't we really just not careful as a community here, or so as a whole, not research community, but software development community?
Oh, thank you for the question. No, so I didn't get a chance to elaborate on what a tangled commit meant in Stack Overflow. In this case, it would be a tangled edit. But it's when the edit would address something other than what that comment would raise, right? So similar to the tangled commits that you've analyzed, the tangled edits would be also like adding additional information. The author's too helpful. They add more information that tries to provide additional information of how the fix works, or maybe they even like add an example of how they change it and then they add an example of how it is now used. So that would be considered tangled because it was not originally what was asked for in the comment.
Okay, so it's basically exactly the same as in source code, but from a different perspective.
Yeah.
Okay.
So I don't think it's that. Yeah, like I said, sometimes it's just the author is too helpful. They provide more information than necessary, but I don't think it's like we're too uncareful as a developing community.
No, I mean, then it's something different. I really thought it would be in code snippets, for example, and then the code snippets that are there are then tangled somehow because they include other logic as well or something.
Yeah.
Okay, thank you.
Yeah.
And we have another question from the audience from Fabio Santos. And the question is for Jenny, and it's how to adapt the signals to gather skills from projects.
Yeah, no, that's a really good question, Fabio. I think one way you could definitely do this is either by, like for a particular project, looking at all the public contributors, mining, like filtering all their contributions that are limited to that particular project, and then just computing the skills that they've kind of exhibited through that. That might be one really simplistic way that comes to mind when I think of this. Although I'm sure there might be other more smarter ways to do it too.
Thank you, Jenny. Masood, did you have a question?
Thank you, Sonia. So I have a kind of follow-up with my previous question. So in certain software maintenance tasks, so for example, for bug localization, so if we follow that manual labeling of the tangle commits, oftentimes it takes a lot amount of time. But if we only focus on that manual labeling, our data set will be pretty small. But when you submit a paper, people will always say that you have a very small data set for this particular task and the result might not be generalizable. So we have these two different competing goals. So Stephen, the question is to you. So what will be your advice in that kind of situation?
Well, okay, shameless self-advertisement. At least for the next couple of years, we have you covered because our data set is not small. We have 290,000 lines. We have 2,200 roughly separate bug fixes in, I think it was 3,000 something commits. So that's larger than almost any other data set that is used for this purpose currently. So if you use our data, which isn't really, really clean because we also validated that really everything is a bug and there are no feature changes in there, that the commit issue links are correct and so on. So at least for now, use our data and you're covered for your publications, I would say. And I think one other way is to actively address this in your publications. So if you use a smaller manually validated data set, stress how much effort it was to create it, measure it, put it there, and then actively discuss the advantages of using manually validated data. So that's what we usually do. That basically we stress, okay, the other data sets have this amount of noise. There are the publications that say this. There's this publication. So for example, for bug localization, there's a great paper by Chris Mills. They found that you get really different results and really a lot of false positive locations if you do not clean your data. And then you put that there. And it's a bit of trust also in the review process. So trust the editors, trust the program chairs to not allow such simple arguments like your data is too small to be the reason you reject it. And I mean, it's trust, so it will probably go wrong. Also, based on my experience, it will sometimes go wrong. You will, but for example, with journal, if it's enough to get in the revision cycle, then you can answer. And even if you get a revise and resubmit, you can still answer. And that's how we usually then, try to fight this sort of issue.
Yeah, thank you. So I have one more question. So you found a bit difference of tangle commits when you analyzed production code and the test code, right? So can you provide a bit more details on that?
Basically, we provided a view with the diffs, the textual diff, similar to what you see on GitHub, but with a left-right view, not in line. And then people just went through there file by file, line by line. We had some nice navigation features that you could skip the line, or if it was a test file, you could just say, okay, this is a test because you saw it's a unit test. We had some nice to have features that we automatically detected white spaces. We actually even pre-labeled some refactorings based on refactoring miner to support people. Well, that actually didn't work out too well because we found some noise there. But then it was just going through it, and it was a lot of work for everyone. If we were unlucky, there were some bug fixes that were really huge, and there we implemented that you cannot skip. So if you drew a huge bug fix, we said, okay, you still cannot skip it, because otherwise we would have biased our data sets towards smaller changes. Often there were actually single lines, so that was really simple. So we added a null check, and then it was just you go through it line by line with your cursor, type 1 for bug fix, type 6 for unrelated improvement, or use your mouse. Probably no one did that because it takes too long. And then slowly we got our data.
Thank you.
Thank you.
Thank you very much, Stefan and Masood. And we have a bunch more questions. Before we go back to the chat, I do have a question for Jiang. Jiang, you mentioned like when you evaluated your model, we saw, I think it was in the last slide or the last few slides, how you evaluated your model on, cancer, like, and all kinds of tasks, right? All kinds of like classification tasks and so on. So I was wondering if any of those, I couldn't really tell from those graphs, but I was wondering if you've evaluated the model also in the context of some software engineering problems.
What do you mean, like the context of software engineering problem? Can you
So
explain more a bit?
sure. So, I don't know, take a task or a task, right? Not necessarily a problem, but a specific task that a developer does, or bag localization, for example. I don't know, effort estimation, or there's a lot of problems that use deep learning approaches, right, and deep learning models in software engineering. And I know that your approach, right, aims to improve upon, right, and basically help generate better models pretty much in a more efficient time, right? So I was wondering if you evaluated, these models that you're producing, or, in the context of a software engineering, uh, in the context of software engineering or a particular task in software engineering, rather than, I mean, if you look at the last few slides, right, you had a bunch of data sets or a bunch of pretty much problems. So each data set addresses a particular problem, right? So cancer detection, I bet, some image recognition and things like that. So did you try, so these are more outside of the realm of software engineering, right? So outside of our field. So did you look at models within software engineering that you could improve upon?
So actually, it, currently in my work, so so currently in my work, so I did not like to, so sorry, like, so like, so
If you want to share your slides, like, with the last slide, if you want to explain on that, I
okay,
mean,
yes,
that's perfectly fine.
let's share my slide again.
So yeah, just like like these, like I see malaria, flower, these are classifications, right? And the breast cancer and blood cell, and I don't know what SD and SL are, but I was wondering, if one of these, categories was related to software engineering.
So like, so my method, so if we have a, a data set that due for the software engineering, so so my method can work on that, like, so because for my method, the input is the data set, and my method will improve the performance of our 2NL in that data set. So like we have better accuracy and lower model complex, lower model complexity. So
Okay, thank you. Thank you very much. Okay, so let's get back to the chat and the questions that are there. So the next question is by Erdem for Henry. Why don't you go ahead and just ask him the question directly?
Thank you. So my question to Henry is, there were 15 pull requests in one of the slides, and 10 of those pull requests were merged to the main. And I wonder, how did you apply your methods to those pull requests, Henry?
Right. Well, the answer in chat, but I'll just say it here. The pull requests were done manually. So we've took comment edit pairs. We looked I looked at all the different rows, and I found comment edit pair that may be simple to do because some of them were quite complicated. Then I actually manually searched GitHub to find matching code that would match the edit part of the comment edit pair. I'd make the change that was in the edit, and then I use the comment kind of verbatim, hopefully, as a pull request message. Sometimes I needed to paraphrase for grammar, and then just submitted it and see what the maintainers did with the pair. And so the idea was like, if we suggested it in like an ID, kind of what I mentioned before in the presentation, if I could just, or if we could just